In this webcast, we're going to focus on finding arc length. To recall the formula, just remember that if you have a curve, the way we find arc length is we take the curve and we cut it up into little bits. Each little bit we then approximate with a straight line segment. That straight line segment has a change in the x and a change in the y. So if I want to find the straight line part, which we denote with a ds, a little bit of arc length, then it's the square root of dx squared plus dy squared. So to find arc length is found by adding up little bits of arc length, which is found by adding up little bits of dx squared plus dy squared. If we were in 3D, we'd etch that on a dz squared. Oftentimes people write a c underneath to denote you're integrating along a curve. Many times curves will be given to us in parametric form, where we have an RFT equals something and an x equals something and a y equals something. If we do that, then the variable that we're going to integrate with respect to is t, so I need a dt at the end, but I can't just put a dt in without dividing by 1 as well. Take this term and divide it through inside the square root, which ends up giving you an integral of dx over dt squared plus dy over dt squared dt. At this point, since I've been told what t is, normally you'll be given bounds for t, a to b. And then you can put those bounds on your integral. That's our formula for arc length. There is a simpler way to look at this. If I calculate the derivative of r, which is velocity, then I get dx dt, dy dt. If I find the magnitude, which is the speed of the velocity, then I get the square root of dx squared, dx dt squared plus dy dt squared. That is precisely the same thing. So I can rewrite arc length as the integral from a to b of r prime, or the integral of speed dt, think, distance equals speed times time. If you want to know how far you've gone, take the speed times by the time. That is essentially all we're doing with this formula. Let's look at an example. Familiar example. Suppose you're going to go around a circle of radius 3. So 3 cosine t, 3 sine t. It's a circle of radius 3, and I'd like to know if t is between 0 and 2 pi. What's the length of that curve? You're probably familiar. C is 2 pi times the radius of the curve, so this ought to be 2 pi times 6. 2 pi times 3, or 6 pi. Well, let's find r prime. R prime is negative 3 sine t, 3 cosine t. The length of that vector is, that's going to end up being a 9 sine squared plus a 9 cosine squared. If I factor out the 9, then I'm left with sine squared plus cosine squared, which is 1. So that's 3. Which means the arc length is integrate from 0 to 2 pi, the speed dt, which happens to be an integral from 0 to 2 pi. I'm going to integrate the number 3. That's a rectangle, which is 2 pi wide, 3 long. We just proved that the circumference of a circle is 2 pi r. We could have replaced the 3 with any arbitrary number, and that would have given us essentially the same formula. As a last example, let's look at what happens if our curve is just a simple parabola. For negative 1 is less than or equal to t, less than or equal to 2. So we're essentially just going to go from that part of the parabola up to, that's a height 4 over 2. Well, the derivative is 1, 2t. The magnitude of that is 1 plus 4t squared. So the arc length is integrate the speed dt from minus 1 to 2. Well, that's the integral of minus 1 to 2. Square root of 1, we'll just take this part and move it over there. dt. That integral is an integral which can't be done unless you use a trigonometric substitution from 113. So we pull out our calculator and say, hey, we're done.